right, welcome back to Beyond Motion. I'm Zach, and here, as always, with my co-host Lindsay.
Hello, everyone.
So today we're gonna go somewhere new, outer space.
Oh,
Not because we're astronauts, unfortunately, although that was always a dream of mine,
yeah, it is unfortunate.
but because space exploration has played a huge role in shaping biomechanics as a science and as a technology. And honestly, some of the breakthroughs that we take for granted today came directly out of NASA's need to keep astronauts alive and moving in zero gravity.
Yeah, that's exciting. And what I like about this theme is that it's not just about astronauts and how cool it is and how cool space is. It's about how biomechanics got pulled into the training, the exercise, how the suits are made, and even the physiology. So I'm really excited. I've seen the rundown on the stories you have to tell, and I'm looking forward to hearing more.
Yeah, and we'll even share something about the how one of Noraxon's very first EMG systems ended up at NASA. So buckle up or strap in, because we are heading beyond Earth.
I'm strapped in.
All right, you ready? Ready for liftoff?
Let's go.
All right. So, first story. So, back in the 1960s, NASA had a problem. They were wondering, how do you train astronauts for a spacewalk on Earth? Their solution was neutral buoyancy training. And by putting astronauts in a pool with carefully balanced weights and flotation, they could simulate weightlessness. Buzz Aldrin was actually one of the first to use this, and even later said that it was absolutely critical to the success of the Apollo EVA, where they were doing a lot of spacewalks. And here's the biomechanics piece. So they weren't just swimming. Researchers were actually measuring their fatigue, the joint ranges in the suits, and how their task performance slowed or changed over time.
It's kind of brilliant when you think about it, because it's the same principle that you discover yourself as a kid, where you're wearing these floaties and you're just trying to like float in the water, do a handstand, and that became basically one of the most important training tools for space.
Yeah, exactly. I mean, that was the aha moment for these guys. You know, the swimming pool became the biomechanics lab for outer space.
Do you think most people even realize how groundbreaking that was? It sounds so obvious now, like, okay, use water to
Right.
simulate space, but back then it was something that was completely new.
Hmm.
And the cool part is it wasn't just like, oh, let's just try it. It's just practice. It was actually data driven. Like they did full research studies on how the suits changed natural movement
Hmm.
and how astronauts adapted their gait underwater versus in microgravity.
Yeah, that's I think that's super cool. And like you said, it's just kind of taking this intuition of like, oh yeah, your body feels like you are weightless when you're in water. And so,
Yeah.
but I mean, even the fact that they could then get all this equipment underwater, submerged, all the suit technology, everything,
Hmm.
just to mimic these scenarios is it's pretty incredible, especially, way back in the day.
Yeah. I mean, it makes you wonder how all the tools that we use today to evaluate biomechanics seem mundane, but decades from now, people could be looking back and kind of thinking, oh, how cool that is that that was used for that application. How cool it is that you were able to simulate weightlessness in space using water.
Water, yeah, exactly. Yeah, that neutral buoyancy showed that biomechanics, it doesn't have to look high tech to be revolutionary, right?
There you go.
So, of course, training in a pool is one thing, but what happens when you actually try those movements in space? And that's where NASA realized that simulation only gets you so far. The real test came when astronauts started building structures in orbit.
So they had these astronauts trying to just build structures in a swimming pool. It's just
Yeah,
kind of funny to
it is.
imagine.
Right, in these big suits and they're,
Yeah.
bopping around with their power tools and
Yeah.
yeah, I can only imagine. And I mean, even just constructing those entire spaces is,
Yeah.
spaces. Uh
in
is pretty
space.
wild. Yeah, exactly. So, this brings us to our second story. So, in 1985, so skip ahead, a couple decades, there was a shuttle mission that was carried out, and it carried out two experiments. They're called the ease access experiments. And so, astronauts, they had to hand assemble 12-foot aluminum trusses in orbit. And cameras captured every single move, and researchers, they measured how the astronauts managed inertia in zero gravity. And so here's the surprising finding. So assembly in actual space was faster than in underwater training. So the astronauts discovered a trick, and they basically found out that sharp bursts of force worked way better in zero G than the slow, careful movements that they practiced in the pool.
Oh, that's interesting. It's funny because, like, I'm just imagining, oh, well, this wasn't exactly what we suspected, but it can't be a bad thing to move faster.
Yeah,
Like, but I mean, the lesson here is clear, right? I mean, they trained for one thing, but they have to be adaptable for what the environment actually ends up being like.
yeah, exactly. Yeah, the biomechanics, it revealed that the strategies had to change completely in microgravity, which I mean to me kind of makes sense. I mean, in the pool you can simulate the weightlessness, but you also have this like frictional element,
Right,
which
like
I've never been
the
to space yet,
yet.
but I don't think it feels the same way, right? So
Totally.
clearly moving and assembling things like that, like uh, there's no way to mimic that, I don't think, in on Earth.
Well,
But
I mean, the fluid mechanics of water don't act the same as air, but then
sure.
space is entirely different from all of those things.
Yeah.
And then obviously the physics of it all, right? You have the friction coefficient that you don't know what it is.
Hmm.
So, but it is interesting. It makes me wonder how often we just assume the results we get from the lab translate to the fields.
Hmm.
NASA spent years refining this underwater training, but then when the real world test came, astronauts just improvised.
Yeah.
So, yeah, it feels
That's
like a product lesson. You could design and test again, but until it's in the user's hands, then I mean, you don't really know what they're going to do with it and how it's really going to work.
yeah, definitely. I mean, you have to be adaptable, you have to improvise, you have to think on your feet. And I think, like you said, it's not necessarily a product lesson. It's probably a lesson for life, even too.
Yeah,
Just
for
like,
anything, be adaptable,
yeah,
right?
plan as much as you can and try and strategize things, but it's not always going to go your way. And so you gotta, find those opportunities to, still be successful in the given
Exactly.
environment. So
It is a good life lesson. Who knew we were dishing out life
I know,
lessons
right?
today?
Yeah, it's, beyond motion for life coaching.
Yeah.
Yeah. But that was exactly what they determined, right? The experiment wasn't just about building trusses, but it was about building a deeper understanding of movement in these new environments, which, for the most part, they really didn't have like great access to
Right.
up until that time, which is, when they were sort of constructing the International Space Station. Um, so yeah, so those EVA construction experiments, they showed how the astronauts could move in space. But movement isn't just about building things, it's also about keeping the human body alive in zero gravity, which I think is a very interesting part of this whole journey, right?
Sure,
And
yeah.
so that's where our next story comes in.
Yeah, I'm actually really fascinated by the fact that the human body just no longer functions exactly the way it would on Earth in
Right.
space because
There's no
gravity
tension.
is doing a lot.
Hmm.
Yeah, so
Yeah.
it's fascinating how they had to come up with all these kind of workarounds to keep you functioning as a
Right.
normal human being.
So you wouldn't just come back to Earth as like a blob of, skin and bone, right?
Right, with like osteoporosis.
Yeah. So anyway, so as we've alluded to, astronauts lose bone and muscle density without gravity. So NASA had a challenge to develop some form of exercise equipment, and they went for treadmills. And Makes sense, get some cardio in there, get your
Yeah.
legs moving, right? Try to experience something that is allows your body to kind of maintain its ability to hold itself up, right?
Right.
So they developed these treadmills for the shuttle and then later the International Space Station. But here's the twist. So when you run in space, the vibration actually shakes the entire spacecraft.
Oh,
So
interesting.
they had to build these vibration isolated treadmills.
Huh.
They had some cool names called the treadmill vibration isolation. um,
It's a cool name.
yeah, exactly. Super cool. And then later, a longer one, a longer acronym, love acronyms, but it was, called Colbert.
Okay.
So, um,
That's cute.
oh, yeah, don't ask me to recite that one. Anyway, so astronauts, they were strapped into harnesses, and that basically pulled them down to the treadmill platform
Okay.
and simulated their weight, while sensors measured their ground reaction forces as they were stepping or running.
Hmm.
And then so that data was then used from a research capacity to give insight into these loading patterns in microgravity and had a big effect and inspiration into some Earth-based rehab devices over time. So
Yeah.
having that information, understanding kind of what happens when somebody is running or walking in these microgravity environments, what does that actually do to, somebody's ability to produce force or experience force, I guess.
Yeah. No, I love that. I think it's great that they had the foresight to be able to plan like, okay, let's not just put people
Right.
out there. Let's
Let's get some
also
data.
build in measurement devices so
Mhm.
we can continue learning and iterating new versions of this treadmill that we had to build, not just for the human on board, but also for the spaceship.
Mhm.
And I mean, they got that bonus data, right? I'm sure the scientists loved having that information to be able to just really drill into exactly how those loading patterns shifted.
Yeah.
But it makes me wonder how close it was to one of our like Earth-based gate labs, one of our many around the
Right.
country, around the world. Like, were they just measuring the ground reaction forces, or do you know if they were also measuring stride and cadence and things like that?
Yeah, so they were. I mean, they were trying to capture as much of that information as possible. I think the idea was to get all this data so that then they could continue to make these informed decisions, create new devices. So yeah, they had load cells that were tracking ground reaction forces. They had accelerometers for looking at stride timing. And I mean, it was full on biomechanics research, 250 miles above the Earth.
So cool.
Yeah. And then the vibration isolation was a biomechanics problem in itself as well.
Yeah.
So designing that treadmill to let astronauts move naturally without transmitting forces throughout the entire station structure was, a feat that they had to solve also. So I wonder if maybe it was kind of dual purpose where like the accelerometers and the force load cells also kind of informed the idea of like, okay, this is how much impact's happening. These are the timing of it. And how do we kind of
Yeah.
adjust the mechanical structure of this thing so that it does isolate this vibration to this one unit?
Yeah. I mean, that's more like you're doing material science, you're
Mhm.
doing a bunch of engineering at that point. But they're at that point they weren't just solving for astronaut health, they're solving for like this whole system as a unit, this like human spacecraft
Right.
interaction. They don't want some guy who's in a completely different part of the spaceship going like, John is up on the treadmill again, like bumping around.
Yeah, I can only imagine what that would be like. It'd probably cause some real big problems.
Yeah.
I wonder how they even figured that out in the first place. If that was like they strapped one on there, just like a regular old treadmill, held somebody down, and then
Yeah.
had them start running, and they're like, "Oh yeah, this isn't gonna work."
I have so much fun thinking about how they must have found out about some of these
Yeah.
things. Like especially, I mean, kind of a tangent, but when you go to like a restaurant or whatever and there's a sign that tells you like don't put this here. It's like the only reason that sign would exist is that
Right.
if someone had done
Someone did
that.
it. Yeah.
And then you wonder like why? How did
Right.
they find out about that?
Yeah.
But
I
this is one
mean,
of those situations where it's like they obviously found out that that would happen, but they strap a regular old treadmill into a treadmill and
yeah,
go
like,
like,
hey,
oh
just
shoot.
throw it in there. It'll be
Yeah,
fine. He needs to
I'm sure
walk.
it'll work.
Yeah. Uh, but no, that's, I mean, credit to them. They obviously had a lot of foresight on a lot of different things, but I'm guaranteed like, 90% of this stuff is
Yeah,
just
trial
trial
and
and error
error.
every time. Yeah, for sure.
Yeah, that's what a lot of engineering is, honestly.
Exactly. Yeah. It's creating problems to solve.
Yes, exactly.
Yeah, so once they had the hardware like the treadmills in orbit, NASA, they realized that they needed more than exercise. They needed predictive tools.
Hmm.
So how will bones and muscles adapt months into a mission? And the answer came in the form of a virtual astronaut. So we're kind of
Oh,
moving into the digital age
okay.
at this point. And so NASA launched the Digital Astronaut Project. And you can think of it as like a virtual human, basically with computational biomechanical models predicting how muscles and bones will adapt in space.
Hmm.
These models, they combined kinematics, kinetics, physiology, and essentially let NASA test all these different countermeasures like, adaptability to resistance exercise or certain aspects of microgravity before putting the astronauts through them. So this is where they started to take the tools, the technology that was available for them, and develop more of that foresight besides doing the trial and
Try
error
it
with
out.
like humans and physical objects.
Totally. I mean, it makes a lot of sense just based on how the technology progressed.
Mm-hmm.
So it's kind of like a digital twin for the astronauts then.
Yep, exactly. That's, you nailed it. And so that's where biomechanics and modeling collided, predicting movement adaptation before it even happens.
Kind of a side note, how close do you think we are to seeing that Earth
Ah,
side, like biomechanical digital twins that can predict injury or rehab outcomes?
that's a great question. I think we're getting close for sure.
Yeah.
I mean, imagine combining wearable IMU and EMG data with predictive modeling. That's not that far off, right? I
No,
mean,
I mean
there's
people
it's
are doing
happening
it
already.
now.
Yeah.
Yeah.
You can obviously use all of that information to estimate the joint loads, risk of fractures, plan recovery rates. And, NASA was doing this to plan for Mars missions. So they were trying to extrapolate this over, months and months in time of these, kind of crazy conditions. And then, the gravity situation on Mars as well.
Yeah.
But anyway, so some of the same methods could definitely be used in everyday clinics.
Yeah, I imagine the resources that NASA had to pour into just creating this digital twin for one astronaut or a few people going up into space. Like, there's probably some, I mean, obviously it's applicable, but it would be maybe challenging to scale it to your layman because they obviously had a lot more to pour into just a few people creating these digital versions of
Right.
predictive models for just those individuals
Yeah, they had
going to
like
space.
5 people or something like that, right? Or
Right.
less than 20. Let's just put it there,
Yeah.
versus masses and masses of individuals or a new patient that walks through the door every single day.
Yeah. And like as we know, human movement is messy,
Hmm.
right? It's so hard to accurately predict what one person is going to do because someone else might strategize a completely different way.
Yeah. Yeah, that's probably even a benefit that they had too from an assumption side is like they knew not like super precisely, but almost exactly what these astronauts are going to be doing every
Yeah,
single day, every single hour. And
right.
so, they could kind of bucket them probably into like high exertion tasks and low exertion tasks. And they
Sure.
could, tune the models to be adapted to each one of those types of categories. And like you said, the volume was just lower. So
Yeah.
they were probably able to get pretty good information there. But I think, obviously with AI and the machine learning algorithms and stuff that are kind of coming online and all the markerless video that's available on cell phones and all
Yeah.
this technology that's, the advancements that we're seeing right now. I mean, it's all that stuff's getting closer and closer. I think the question is just going to be like, what's the accuracy? Like how reliable
Yes,
is it?
totally. I mean, we've talked about it
And is it
before. It's
valuable?
right. There's so much data out there, but we're still kind of in that phase where we just have a bunch of data, but
Hmm.
nothing to do with it.
Yeah.
And a bunch of data that, is technically measured maybe by the same principle of device, but
Right.
with very different specifications and accuracy levels. So, what can you trust? What can't you trust?
Yeah.
But I mean, that I think just even that topic, as we're discussing how NASA created these predictive models, obviously they had access to top of the line
Sure.
technology to be able to measure these things. Whereas clinics, are a little bit more price sensitive. They don't always have access to top of the line products,
Yeah.
which is why, you see these app-based companies pop up with, different things to measure motion capture all the
Mhm.
time, but, the accuracy could be very variable between those products.
Right. Yeah, and I mean overall though, I think the parallel here is that like the technology is in the hands of these people way before it's in the hands of like the community at large.
Oh, totally.
And so they sort of go through the struggles of figuring out like, can it be used? How should it be used? The refinement of some of the algorithms, the iterations of the technology from being giant pieces of equipment to being, handheld. Uh, and so that's what I think is maybe more of the parallel that we're seeing with this particular set of stories is like it's coming from the need to kind of protect and make these astronauts more resilient
Sure.
and have them move and understand their bodies in these crazy environments. And then sort of once they use that up and they solve those experiments and they're on to their next challenge, then it's like that technology kind of trickles its way down
Yeah.
into
Yeah.
the real world, so to speak.
Yeah, it does. But so just thinking back to our previous podcast,
Hmm.
and those of you who haven't listened to our biomechanics in the courtroom yet, go ahead and give it a listen. It's a really fun one.
Yeah.
But I'm kind of thinking about what happens when these predictive models start getting used in insurance claims in the courtroom.
Yeah.
It feels kind of like a natural continuation of that last podcast, but it's interesting to think about, right? I mean, technology is improving. How can it, if can it in general be used to prove that something would have happened if yada yada yada?
Right.
Could someone have gotten hurt if this company didn't take every measure possible to mitigate the risk of building a bridge this way? I don't know,
Yeah.
right? It's a
No,
it's a weird rabbit hole.
I mean, it's definitely bridging the two episodes for sure. And I mean, we could probably spin off another 45 minutes just talking
Yeah,
about that again.
probably.
But so we'll table that one for maybe the part two of biomechanics in the courtroom. But
Yeah.
regardless, I mean, it's clear, right? The science and the context always go hand in hand, and so you can't. If you're going to be making these assumptions, then they have to be made in, controlled situations. And if you release those out into the wild, then, take it with a grain of salt, right?
Yeah, totally.
So we'll see. I don't know. I mean, I think that's the exciting part, and we kind of get to be on the forefront of that in a lot of ways,
Yeah.
and see how this morphs and participate in it as well.
Yeah, for sure.
So we got our next story here. So of course, you can model astronauts all day, but they still need to wear the suit and survive outside in space. And the suit itself was actually a pretty big biomechanics challenge as well.
I can imagine.
Yeah.
These things are huge.
Yeah. Yeah. So, let's take a look at how the ergonomics became mission critical when designing these spacesuits. So spacesuits, they are walking biomechanics puzzles. The early Apollo suits were completely custom fitted, but the shuttle suits, they shifted to more of like a modular sizing,
Hmm.
and that required huge anthropometric data sets, body dimensions, ranges of motions, all ergonomics. And turns out some of these early designs actually restricted shoulder flexion so much that astronauts could not even reach the overhead switches. And so biomechanics data drove redesigns of the suit, joints, and the gloves.
Yeah, I mean, the ergonomics wasn't optional at that point. If they
Yeah.
can't reach the button they need to reach, then the mission's over.
Yeah, it's gone. Yeah, hopefully that was also something that they didn't trial and error with in reality.
I know. I mean, it's the same thing as, if you're a pilot operating an aircraft, right? You have switches above you, you need to reach. There are ergonomic studies on that,
Yeah.
but you have this extra barrier of like, oh, you can't just wear clothes. You have
Yeah.
to wear this huge suit.
Right. Yeah, and it's got its own requirements to keep the pressure and, keep you oxygenated and
Yeah.
temperature controlled and all this stuff. But
Yeah.
anyways, I mean, it was, obvious, right? The biomechanics, it was mission critical engineering. And
Oh,
so it's,
definitely.
presented some fun challenges, I bet, for these folks to figure out.
Yeah. So here's what I'm curious about with those anthropometric data sets. Do you think we're still using those today, or has commercial space flight created a new set of standards? Because a lot of the anthropometric data we're familiar with is very old.
Yeah.
So it just makes me wonder if, NASA has ever shared those with the world.
It's a good question. Yeah, I don't know. Maybe. I think that it'll be interesting, like, as we're seeing like space flight become more of a consumer level type of thing, right? You
Yeah,
have,
they can't build custom suits for everyone, huh?
yeah, so, or maybe they can, but it's, just increase the cost, right? The idea, I think, is
Right.
eventually that this is something that's somewhat economical. Um, so either those data sets are continuing to be added to and they're figuring it out,
Yeah.
again, more technology to be able to use. They've got all these like body scanner options now. And
Oh,
so,
yeah, totally.
maybe they can get access to that information a little bit easier than they could in the past, where you don't actually have to have somebody like physically measuring, but you just stand in a space and the cameras and the sensors rotate around you and then produce your digital twin.
I
Yeah.
exactly.
But anyways, I mean, yeah, that human-centered design is going to matter, even more when the astronaut body isn't limited to just these elite pilots.
You have your normal human body.
Yeah, 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 and all its, shapes and sizes, right?
Exactly. Yeah, I mean, that is an interesting challenge. It's just, again, it's just interesting to think about how deep this rabbit hole can go when you consider, like, oh, yeah, space flight should become a commercial thing eventually, but there are all these factors to consider before making it a thing at all.
Mhm. Right.
And it's just down to like, oh, what are they going to wear? Like, they have to wear a spacesuit.
Exactly. Yeah, it's not just the rockets, but that was
Yeah,
obviously a big portion of it, but then
totally.
it's the little details, and oftentimes those are the ones that matter the most.
Exactly. Hmm.
Uh, I don't know, those Blue Origin, I think that's what it's called. Jeff
Yeah,
Bezos, his rockets that sent people up. Those spacesuits didn't look like they were super spectacular, but
they didn't.
granted, I don't know if they really were in true space.
Yeah, like
They
I
weren't doing
don't
any spacewalks, that's for sure.
exactly. Yeah. So it depends on what the need is, I
Right.
guess. So if you're not going out into space, obviously that additional spacesuit component isn't necessary. But what about like safety, right?
Yeah.
If you board an airplane, you always have the flight attendants giving you the spiel on where to find your life vest
Yeah.
and how to inflate it and to
Your
help the
oxygen
person
mask.
help yourself before you help the person next to
Yeah.
you. Like
Another life lesson.
another life lesson,
Just
right? Listen to the
put
flight
put
attendants.
it in the bank.
But thinking about commercial space flights, right?
Sure.
Like you're gonna be in a rocket ship and your space flight attendant is gonna be like, all right, you have this custom made suit underneath your seat that you'll take out in the event the rocket blows up and you end up floating through outer
Right.
space.
In case we need you to fix a panel on the outside
It's
of
gotta
the
be
ship.
like a safety consideration, right?
Yeah.
Like, is it just okay, you're in space, if something happens, you're just Out of luck.
Yeah, you got your sweatpants on and
That's it.
that's it. You're done for. At least you're comfortable.
But you
Um,
have to sign a liability agreement
yeah.
before. If you die, you won't sue them.
uh yeah, it's such a far-fetched thing to even think about too. Like just,
It just feels ridiculous.
obviously all of our, human space travel has been sort of near Earth in a way, right? Like the
Yeah.
International Space Station, but the goal, especially at this point in time, is, to try and develop these systems that can take us into deeper space.
Yeah.
And that's going to, of course, start with, these elite group of people. But at some point, does it actually make it to be like kind of consumer level? And so all of these kinds of effects, both that we're talking about from the exercise side of things, the physiology, the ergonomics,
Yeah.
the everything, has to somehow be like, made possible for the masses and
Right.
not just this small subset of people. And
Yeah.
so, I mean, again, grateful that they're figuring out these things, but maybe that's why it takes, decades and decades and decades
Oh, I'm
for to just
sure.
iron out some of the smallest details.
Oh, exactly. It's like they need to solve an entirely new set of equations to replicate like Earth-like environment inside a spaceship so they don't have to do all those things or
Yeah.
something.
So that kind of is an interesting segue for us because, even with better suits, astronauts, they still faced an unexpected enemy, which is their own
Hmm.
bodies. And
Okay.
so space motion sickness could cripple
Oh,
a mission. And that's when NASA, they really turned to biomechanics in a totally new way through biofeedback.
couldn't
And
just give
so
the astronauts Dramamine.
no, it doesn't work as well, I guess. But same thing, right? Like if it this is we're talking about regular old people that, are gonna be going up here. It's putting your body through some crazy demands.
Oh,
So again,
totally.
they're fleshing these things out from top to bottom. And so this story is one with Dr. Patricia Cowings, and she developed what's called autogenic feedback training exercise, or AFTE. And astronauts, they often get space motion sickness. And so Cowings taught them through biofeedback techniques to control their heart rate, their muscle tension, balance responses, and it worked. They adapted faster and had fewer symptoms.
So biomechanics meets neurofeedback.
Yep, you nailed it. Yep. And of course, that spilled over into Earth applications for vestibular or disorders and other ailments that people were having with balance and vision and dizziness and all of those things.
Yeah, it feels like the same techniques they teach you. What's that sport called in the Winter Olympics? Biathlon, where you're like long distance skiing and then you have to slow your heart rate down to shoot a
Oh,
rifle.
right. Yeah. I
It's
think that,
like,
yeah, biathlon. Let's go with that.
I think that's what it is. But if I'm wrong, correct me,
Yeah.
internet.
Yeah.
But I'll look it up later. But you know what I'm talking about, right?
Uh-huh.
That's a
Yeah.
sport.
Yes.
But it feels like the same techniques, right? Like you have to be able to control these things that feel like it's your sympathetic nervous system, right? Some things that are very can be controlled by emotion, can be very variable. So, but I mean, that's interesting because what strikes me about this whole technique is it feels like kind of the grandfather of wearable devices. Like astronauts are using these sensors and feedback loops to control their physiology, but
Yep.
it's all happening in their brain. Decades before Fitbits or heart rate variability monitors or anything like that could give you that information. It's like you have Dr. Patricia Cowings just telling these astronauts to be a little bit more tuned in to
Aware. Yeah.
aware of their body, aware of how they're feeling without having the data to go with it.
Yeah, I'm
So,
sure they were hooked up to some stuff. I mean, definitely Earthside, right? Like while they were
Earthside,
practicing,
right?
right? I don't
But
know
you have
about
to be tune yourself to like say, okay,
this
look
is
at the
what this feels
screen.
like.
Yeah, this
Yeah.
is what
Hmm.
this feels like.
Yeah.
So, which
Yeah.
I'm sure people do with enough data with their wearables, right? I mean,
Yeah,
I've
definitely.
definitely looked at my my Garmin watch with my heart rate monitor and gone like, oh, I wonder
Yeah.
if I could like calm
Yeah, can
myself
I
into
slow my
slowing my
breathing
heart
down?
rate.
Yeah.
Yeah.
Yeah, definitely. Yeah, and it seems like this was the same method that was used to prevent astronauts from puking in zero G. And so that's great. And it's helping patients with balance disorders walk straighter here on Earth too.
Hey, that's
And
great. Yeah.
yeah, complete full circle moment.
Yeah. So NASA is figuring out to solve a problem, but it's trickling down into, just regular use.
Yep,
I'm
exactly. That's the theme, right? Is that
That's the theme. Yeah.
they've
It
been
just
doing
makes me
this.
wonder how, I don't know. It just makes me wonder how we had to start at solving this crazy thing that isn't even possible in like normal human life. And you had to start way up at the top there for it to trickle down into like, oh, what about that guy who
Yeah.
just like has a vestibular disorder?
Sure. Or like, that
You couldn't just
marathon
solve it
runner.
there. Yeah.
Yeah.
It's just it's funny to me how you have to kind of go past the bounds of normal use in reality to like really test the extreme scenario and develop for the extreme scenario for it to even come back
Mhm.
down to the normal
Right.
area. It's
Yeah.
just it's funny to think about.
Yeah. It makes you wonder if it would work the other direction.
Right,
Right.
exactly.
Maybe.
But it seems like a full circle moment
That's
at
right.
least.
Yeah, and speaking of full circle moments, so Noraxon itself has a small but proud role in all of these stories,
Oh yeah.
because one of our very first EMG systems was actually installed at NASA,
Hmm.
and they used it to study astronaut muscle activity during training and adaptation exercises. So it's kind of amazing to think that the same company that now makes tools for these labs and clinics once helped strap some gear into these NASA experiments as well.
Yeah, it makes
Little pat on
sense.
our own back
There
here.
you
Yeah.
go. And we weren't around at that
No.
time, but yeah, it's always kind of an interesting story to hear. That was, I believe, is the first system sold in the US
Oh
was
yeah,
to
that's
NASA.
right. Yeah,
Um,
that's a good
so
sale.
it has a good sale. It was
Yeah,
a pretty good one.
yeah.
And here we are, a
That sets
US
the
based
benchmark.
company.
That's
That's the
right.
benchmark.
No, that's great.
That's awesome. Beyond Motion goes beyond Earth.
Oh.
I love it.
All right. So today we've seen biomechanics underwater, in orbit, inside treadmills, in computer models, in suits, even in astronauts, their own physiology. So, and space travel clearly didn't just need biomechanics, it actually helped push biomechanics forward.
So after all that, if you had to pick the single biggest, aha moment biomechanics got from space,
Hmm.
what would it be?
Good question. I'd say, I think for me, it's realizing that you can't assume that these Earth biomechanics actually translate, and each new environment forces new science. And I think that's what shaped biomechanics into sort of the adaptive, context-aware field that it is today.
Yeah, and I agree. I think that's a really big takeaway for us as product developers too. Like the next environment might not be microgravity,
Hmm.
but for aging populations, VR, AI driven clinics that utilize this information and create these simulations, I think the lesson is all the same. You have to measure, not assume.
Yeah.
So
Yeah.
it's kind of fascinating. Just remember that the same lessons can apply to all these different scenarios.
Yeah. Well, thanks for joining me on this fun-filled space journey, space and biomechanics journey. Of course, all of our listeners out there, make sure that you are subscribing to the podcast and listening to us and liking everything. Follow us at Noraxon USA on all the social media platforms. And until next time, keep exploring.
See you next time.